Hi everyone, welcome to my presentation on doing BPF programming using Rust. This will be a moderate introduction following along from my previous videos of gentle introductions to BPF. And it's moderate because it's a little bit more advanced than those videos. So the agenda today is that we're going to set up a Rust environment with the tools that we need to get our work done. We're going to set up a virtual machine to do our work in or to test our applications out with. We're then going to code up a BPF program. Then we'll code up the Rust program that uses that BPF. And for extra credit, we'll do some BPF LSM stuff as well. So a few assumptions about this video. The first assumption is that you're familiar with Rust. This isn't going to be an introduction to Rust video. There's plenty of other introduction to Rust videos out there on the internet. One of the channels that I like for intro to Rust videos is a guy calling himself Tensor. I like his videos about Rust. And that another assumption is that you can already install a virtual machine by yourself, and you know a few things about the kernel and doing you know a few things about intra-RAMFS also. I have previous videos about these subjects. And another thing is that you've watched some of my previous gentle introduction to BPF videos. This is going to be a more advanced video. You can probably follow along with what I'm saying, and you can probably learn a few things. But watching the previous videos will be helpful for you. So let's get started. The first thing that we're going to do is Rust up. And Rust up is one of the best ways to get your Rust environment. Each distro will allow you to apt-get Rust or DNF install Rust and cargo as well. But I like using Rust up because it's nice and easy and it's generic upon all the distributions of Linux. Then we're going to download the Git version of libbpf rs. We don't want to use the crate.io version because it's a little bit old and there's some new features that we want to use. Just a warning, libbpf rf is still alpha or beta quality, and the APIs that it is using is subject to change. But we're going to go with what we have right now. So after that, we're going to cargo install libbpf cargo so that our cargo package manager is able to use certain features that libbpf rf gives us. And then we're going to set up a new project and put a few things in the cargo.toml. So let's do that right now. So I've got my browser all ready to get me Rust up here. So all you have to do to get Rust up is copy this, and we're going to paste it into a terminal. And we're going to follow the instructions by just pressing enter, basically. So the next thing that we're going to do is make sure that our shell has this cargo environment stuff, and that our bash rc has .cargo.bin inside of it. So let's take a look at our bash.rc. And you can see in my bash rc, I've already done this work. So these are the things that you'll need to put in your bash rc if they're not already there. So that's path equals the previous path plus home.cargo.bin, and our source, we source the cargo environment. So with that all done, I'm going to ensure that bash rc is run on the terminals that I have up right now. So we've got all those things in. And the next step is that we're going to get the libbpf rs. So I've also got that already in my Firefox window here. So we're going to grab the code, and we're going to go into our code directory and git clone it. right. The next thing that we want to do is cargo install the libbpf cargo command. So we're going to cargo install libbpf rs libbpf cargo. And this will take just a moment because it's got to compile it up and stuff like that. Oh, this is interesting. This is a new problem. There we go. Just make sure that you're in the libbpf rs directory when you do your cargo install. All right, and the last step that we need to do here is that we're going to do a cargo new my BPF. All right, and there's a few things that you need to put in your cargo.toml. This anyhow is for a macro called bail that libbpf-rs uses. So we need that. We need anyhow bail. And it's also nice to use the anyhow result because it's a nice easy to use result type that anyhow can give us. I've already got these things ready, so let's go into the mybpf directory and open up the cargo.toml, and then we will copy in our dependencies. And let's do a cargo build just to make sure that everything builds. And cargo run, we should get a hello world. Great. Okay, so the next step that we need to do is set up a virtual machine. Now we want to use a virtual machine because we have to alter the kernel boot up command line for the extra credit part of this this video. And that's annoying to do on your bare metal machine. So we're just going to use a virtual machine because it's easier to develop using the virtual machine here. Now, libbpf sys, which is one of the dependencies of libbpf rs, doesn't compile with musil, so we need to use the standard glibc to compile our project. And I'm pointing this out because while our BPF code is going to be CORE or CORE, which means compile once, run everywhere, our code for our Rust code, which uses libc, is not going to be compatible with older systems. So for example, because I'm coding this on a Fedora 33 machine, it's not going to be compatible with the CentOS 7 machine. And that's not because the BPF isn't going to work. It's because the Rust code that links against glibc isn't going to work properly. So as I said before, I'm going to be using Fedora Server 33 as my virtual machine, and I'm using Fedora Workstation 33 for my main bare metal host machine. So after installing and updating, which I'm going to leave as an exercise to you, to install Fedora, there's lots of videos on the internet about how to do that. Once we install Fedora, we need to grab the kernel and the init ramfs. And we also want to make note of the command line options from a dmessage. So let's do that right now. So I have over here in my virtual machine directory, I've already installed a Fedora 33 server machine, and I'm going to give that a run. So I've called it Fedora serve Fedora, and I'm going to make sure that I can attach to it on port 2222 for my SSH. So I'm going to run that up. And then I am going to SSH to the local host on port 2222 once it's up and running. And what I want to do here is from boot, I want to copy VM Linux 5.9.13 to my home directory. I'm then going to sudo chown it to my user. And then I am going to rename it from VM Linux.5.9 blah, 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 blah to just VM Linux. And then I'm going to do a similar thing for the init ramfs. All right. And then we are going to escape out of that and secure copy them. To the Fedora serve directory. And the same thing for the init ramfs. And let's give this a boot up with those. Oh, and one more thing. We need to do a D message. And we've got our kernel broke. That's interesting. Anyways, we want to take the command line options that Fedora uses to boot up because we're going to add things to this. So what Fedora does is command line options. Where are they? Interesting. This is a little different from what I had before. Oh, okay. And we want to copy this out. Copy that, and let's store this over here. Now this is a little bit different from what I was expecting, but we'll give it a try. So let's shut down our VM. Oh, because I'm on my home machine. That's why I'm having a problem here. Go back into the SSH and do a D message, and then we'll grab the kernel command line, which is this. Now I've hacked with my system before, so just ignore that. That's incorrect and it's not default. And we will replace that with this. Okay. Now we'll shut down the virtual machine. And let's boot up the virtual machine now. Supplying the kernel that we just downloaded, VM Linux, and the init ramfs of init ramfs, and then we'll give command line options of what we just copy and pasted. And hopefully this boots up just fine. Looks like SE Linux wants to do a little bit of relabeling on my hard drive. So give it a second. All right, and we've booted up, and let's get ourselves into local SSH, and we can do stuff. Great. So I am now going to shut down the virtual machine one more time after our test is complete. And we will move on to coding up the BPF program. So one of the differences between this video and my previous videos is that we're going to code against libbpf rather than BCC. libbpf promises co-re, which is compile once, run everywhere. And I'm not sure if I'm pronouncing that correctly, if it's co-re or C-O-R-E or core. I like to call it co-re because it's fun and it's not, people might get confused if you say core. But anyways, what co-re does is it compiles your BPF program at compile time into an object file, which your Rust program will then take, package it into the Rust program itself, and then use that object file to insert into the kernel at runtime. This differs from BCC. What BCC does is it takes a string, a raw string of your BPF code, and at runtime it compiles it into an object and then injects it into your kernel. So the differences here is that co-re uses a new technology called BTF, BPF type format, while your kernel needs to be compiled with BTF enabled for it in order to use this feature, while BCC does not need to do that. But the problem with BCC is that the program you ship, you're actually shipping an entire compiler. You're shipping the actual BPF LLVM compiler inside of your application, including Clang and things like that. So your binaries are very bloated when you use BCC. And also, one of the things that co-re promises is that because it uses BTF, the things that you know about the structures internal to the kernel are going to be able to be used on every kernel that every kernel that you're using the co-re program on. While BCC, you might have problems, especially if you're using kprobes, because the kernel structures change between versions. So saying all this, it's mostly the same. The main difference is in how you do maps, your BPF maps. So how you exchange information between your user space and your kernel space programs here. We won't be looking at maps today, but the change is pretty straightforward and it's fairly obvious from the documentation. One other important thing to note, which caught me up a little bit when I first started programming using libbpf rather than BCC, is that the print k function that you use has changed from BPF trace print k to just BPF print k. So one of the first things that you need to do in order to use BTF is that you have to dump the BPF structures from your VM Linux into a header file called vmlinux.h. So we're going to do that right now. And I'm going to get myself into my BPF program, and then we're going to go into the source directory, and I'm going to make a directory called BPF. And inside of BPF, I am going to run this command. BPF tool. Oh, of course, I am still. Am I on? Which am I? No. Okay. There we go. And we have this header file that our BPF programs will use in order to know about structures internal to internal to the kernel. So let's take a look at that. And oops. Oh, I've screwed up all my my stuff here. Sorry about that. Give me a second here. That's good enough. So as you can see, this VM Linux.h just contains a bunch of stuff from the kernel about structures and things like that. So let's not worry too much about this. We just need it to exist in order to continue. And that over there. So the next thing that we want to do is we want to code our BPF code. Now we're just going to be writing basically a C code here. And it's going to be, we're going to do some very simple stuff. So I want to we're going to call this exec.bpf.c. Now libbpf-rf is very explicit that you need to give all your BPF programs the extension .bpf.c. And I'm not quite sure why it needs it, but it needs it, so we'll go with that. So let's open up that file, and we start off by doing an include of the VM Linux.h. And there's two helper files that libbpf also gives us. And those two helper files are, I believe it's called include bpf/bpf helpers.h and include bpf/bpf tracers.h. And let's double check that those are the correct names. So let's go back into the libbpf-rs GitHub repository, and we're going to take a look at one of their examples called run queue slower. So jump into their BPF source, and they're only using helpers, but tracer tracing is what I want. All right. Tracing. Okay. Let's jump into the libbpf-rs code here and see if they've got that tracing file. So we want to search for the name tracing.h. See if they've got it. No. What about libbpf, the C part of libbpf? See if they've got that BPF tracing. So they do. Okay, so, and this is what it gives us. So a lot of these helper functions are useful. And one of those helpers should be BPF prog. Yeah, so it's a convenience wrapper that you can use. Okay. So we've got that done, and now we're going to do something similar to how the run queue slower is doing things, but we're going to be doing a much simpler program here than what run queue is doing. So the way that you do BPF functions using libbpf and libbpf-rs is that you do this section macro, and then you tell it what type of thing you're attaching to. So in our case, we're going to attach to a trace probe, and that trace probe is going to be for a system call, and I think it's system call S, system calls, and we're going to attach to the system call. Let's take a look at what system calls we have available to us. We don't have Sue on Fedora. And we want to find them in sys kernel tracing events, syscalls. Then we'll take a look here, and we want We want sys enter exec VE. So let's do a LL for a sys enter exec VE. Yeah. So we're going to look for sys enter exec VE. And then it's going to return an int. We'll call this, we'll use that helper macro, and we'll call the function enter exec, and then we're simply going to use a void pointer to get our context here because we won't be using it, and we will use a BPF print k and say entered exec and return 0. And let's do an exit as well. So sec trace probe syscalls sys exit exec VE. And again, and I've never actually tried to see if the BPF prog works with libBPF RS. So we're all learning something right now in this video. And one last thing that you have to do here is we need to set our license to GPL. And that's so that we can use things internal to the kernel. All right. So we've got that done. Now inside of our project directory, we're going to do this cargo libbpf build. And it did not like that BPF prog, so let's revert and just do it the old-fashioned way of there we go. Now inside of the directory, that's the my BPF. Inside of source BPF, you'll notice that, oh, there's one more thing that we have to do here. So what we've just done is inside of the target, you'll notice that there's a BPF directory and our BPF code has been compiled into an object. So now we're going to issue a cargo libbpf gen. Oh boy. What mistake have I made here? Search through the video, go back to see if I used the path switch. Because this error that you see here, when you issue the libbpf gen, is one of the reasons why I'm using the main GitHub repository rather than the crates.io version of libbpf RS. So I might have made a mistake there. So hopefully, if we go back into my BPF, we can cargo libbpf gen. There we go. Okay. So inside of our my BPF area, inside of the source BPF, you'll now see that there are two Rust files created. This exec_scale.rs and the mod.rs. And these are auto-generated, and they have a bunch of stuff in them that correlates to the BPF program that we just made. So one of the things that I don't like is that there doesn't seem to be a cargo lib BPF clean. And cargo clean does not delete these RS files. So what I do is I usually just make a makefile to manually clean out these things and to do the cargo stuff. So let's make a makefile here. So let's CA makefile. And I've already made most of a makefile before, and it's a very simple makefile. So I'm just going to copy and paste it from a previous project. And there's going to be a few things here. So the first thing that's going to happen is that we're going to do that cargo lib BPF build. And then we'll do the cargo lib BPF gen. So that will compile up our BPF code and the skeleton code that uses it. And once we've got our Rust code all set up and working, this main will cargo build everything for us. So it will make our Rust code and include the BPF objects into it as well. Another thing that I like to do is have that BPF tool call automated so that it makes my vmlinux.h file every time. And then I have some clean stuff where it does the regular cargo clean that cleans out our Rust stuff, and an RM that cleans out those auto-generated Rust files and the vmlinux stuff. Let's save that and do a make clean to make sure it works. And those the vmlinux and the skeleton Rust auto-generated code is gone. So now let's do a BPF, a make BPF to make sure that our BPF stuff is all made. Make scale. So we've got our skeleton, we've got our vmlinux file, and we have got our object. So let's start with the Rust code. The Rust code is simple, but it's not extraordinarily straightforward. So we're going to change our main.rs. And the first thing that we want to do is include that, is use that anyhow stuff. So we're going to use bail and we're going to use result. The next thing that we want to do is mod BPF and use BPF everything. So the BPF stuff comes from this mod RS. It's I don't quite understand how it knows that we need to use BPF and mod BPF, but I'm not going to worry too much about it. It's one of the magical things that cargo lib BPF does for us. So we've got those things inside of our main.rs. So let's just cargo build, make sure that it compiles again. And we've got some unused imports, but that's fine. Everything's compiling up properly. So get back to that run slower, because we're going to take a look at how run slower does things, and we're going to adapt our program based on that. So the main function of run slower is pretty simple. The first thing that they do other than like getting command line options, we're not going to worry about that stuff, is they create their skeleton. Now, since they've called their BPF run queue slower, their builder is called run queue slower skell builder. Ours is going to be called um, exec skell builder. And the way that you can make sure about that is open up the skeleton file, and you will find this structure, exec skell builder, and the functions that it implements. So we are going to, excuse me, got the hiccups. So we are going to call the default on that. And then we are going to use that exec builder to exec builder dot open dot load. And because we have used this this question mark feature, we need to use the next part of anyhow, which is their easy to use result. So let's compile that, make sure it runs again. Expected a standard result and I'm using the anyhow result. Why did it not pick up my anyhow result? Should have picked up my anyhow result. Oh, it is. We just haven't done our proper return. There we go. So again, if I give this a cargo run, we should just get a help. Right. We have to be super user. So sudo target debug my BPF. We should get a hello world here. Oh, there seems to be a problem. We have reached a limit of the size of our BPF program. This is one of the differences between libbpf and BCC. When you use BCC, behind the scenes, they do an increase to this rlimit memlock, but libbpf doesn't do auto automagically for you. So you have to code that up yourself. Luckily, the run queue slower has already done that for us, and they've done it inside of this bump memlock rlimit function. So let's grab that and put that in our program and call it before we do anything else. Bump. And let's compile that up again. Give it a run. Doesn't like something with failed to load program, trace probe, syscall, sysenter, exec VE. It is exec VE, right? Exec VE, yes. Syscalls, trace probe. Is it trace probe S? What did I call it before? Trace point, syscalls, sysenter, exec VE. Trace point. Oh, we need to recompile the BPF code, not the Rust code. So let me do a make clean, make skel, then a cargo build. And my make file should have that all ready if I just do the make main or just regular make command. All right. And test this out. Good. Okay. So we've got that going there. Finally. And let's close down these exec.ve stuff and go back to our main. So what we've done is we've loaded up our BPF code and then we immediately exit out of it. So we don't want to do that. We also want to attach to our code. So exec dot attach. Still good? Okay. So we're loading up our BPF code, but then we immediately exit, so we're not doing anything here. So we want to just add a little bit of a sleep here, so that we can take a look at the trace pipe to see the things that are going on. So the way that we do a sleep in Rust is that we're going to let 10 secs become standard time duration from secs, and I think it's just the integer 10, and then we will do an std thread sleep for that 10 secs, and that should delay us for 10 seconds. Let's make that and run it again. And we're going to be sitting there for 10 seconds. Now in another window, let's cat on the syskernel trace pipe. And just sit there. And in here, we're going to do things like LL. And over here, move that up, we can see that we're entering exec and exiting exec, just like our BPF code wants us to do. So we've just done our first BPF program, printing out stuff as exec.ve is run. So when exec.ve function, the syscall exec.ve is entered, we get the entered exec, and when it is exited, we have the exited exec. So let's run that one more time. And do some LL stuff, and we can see the things firing. So that's great. And we've done all of our Rust code here. But what we haven't done is our extra credit. So our extra credit is let's do some LSM work. And I have a previous video on what LSMs are. Normally an LSM is a security module that it's not so much a kernel module like your NVIDIA graphics driver or things like that. It's a module that's still internal to the kernel. It's not something you insert or remove. However, when it comes to BPF, we now have the ability to insert or remove an LSM that we compile, and that we're running this from user space rather than from kernel space. So let's do a sec for LSM, and we need a list of the LSM LSM hooks. So I've gone through this sort of stuff in a previous video, but if you just follow along here, you'll see you'll kind of get the gist of what I'm doing. So I'm going into security, and I'm looking for the security H file that defines, actually it's probably in UAPI, but let's just take a look for, let's look for security BPRM check. All right, so we're looking for the thing that implements the security BPRM check. So that's include Linux security.h. So here's a big long list of all the security hooks inside of the kernel. And we can attach to these as well. So we want to use the security BPRM check. Now, for some reason, to hook on to this call, we're going to be hooking onto BPRM check security. And I'm not sure why that is. It's just the way it works. And we're going to call our function LSM hook. And it's going to take a struct to a Linux underscore bin PRM, and it's a pointer, and they call it BPRM. And in here, we're just going to BPF print K LSM hook called, and we're going to return 0 saying that everything is okay. Please continue on with your function. So we will compile our program again. And we're listening on the trace pipe. And we're going to run this. Now, one thing that you notice is that we're not calling this LSM hook. Now, this LSM hook should be called upon, well, I'll show you exactly where. Let's jump into this code. And it's in the exec.c file. And it's inside the search binary handler, which is part of the follow through from exec.ve. And it's doing this security check right here. Basically, if you fail the security check by returning something other than 0, your exec.ve won't get past the search binary handler, and therefore you won't find what type of binary you're running, and you won't run your binary. But the problem is, we're not even getting into that inside of our BPF code here. And the reason for that is because the BPF LSM has not been enabled on our host machine's kernel. So this is why we need to use a virtual machine, because we're going to change the LSMs inside of our virtual machine's kernel. So let's get back to our virtual machine area. Inside of VM, not VMware, code VM, and that run command that we've got somewhere in our history here, we're going to add to the kernel command line that we're going to use LSM equal to SE Linux, because Fedora uses SE Linux, and BPF. So we're going to be booting up our VM here, and we're going to transfer our target /y. Why is autocomplete not working? Because I didn't give the proper port. Target debug my BPF into the local host. All right, so we've uploaded our program, and let's now SSH into that machine. And we see that there is my BPF here. So let's give this a run. And in this window, how am I going to order the windows here? We're going to move that over. move that over here. We'll move this up here, and we'll zoom in on these two windows. And on this window, we're going to sudo cat on sys kernel tracing trace point, trace pipe. And in this window, we're going to run the myBPF program. So it's running, but we're not seeing anything. So why is that? There we go. So as you can see, we're calling the LSM hook, and we're exiting. So that's great. But we're not actually LSMs are to prevent things from happening. So let's prevent things from happening. Let's do a -16 here, which is an Erno. So we want to find the Erno list. What's a good Erno list? I usually have this bookmarked, but I've just set up this machine recently and haven't bookmarked the proper Erno. Does Cisco have a good Erno? Not really. This is a good one. So let's bookmark this. We're going to move that to next toolbar. All right. So we're returning -16, which is eBusy. So now, after we compile once again, after making our -16 change, and secure copy it, now when we run this code, we should actually be prevented from running any executable. So you can see now that I'm trying to run ls, I get this device is busy. So we've got ourselves the beginning of doing a BPF-based LSM using Rust. So thank you very much for joining me. I hope you forgive some of the bugs that we saw going through this code. I hope you've learned something. So have a good day or a good evening or a good morning.